Olivier Carton from IRIF at the Paris Cité University, and he will speak to us about Mahler equations for Zeckendorf numeration.
Okay, thank you for the introduction. Hello, everyone. So I will present, yes, a joint work with Rim Yazawi from the Queen Mary University of London. And it is about Mahler equation in Zeckendorf numeration. It's an extension of automatic sequences to the setting of Zeckendorf numeration. So actually, I cannot switch to the next one. Yeah, okay. The outline of the talk will be the following. First, I will recall what numeration systems are and what is automaticity. I think everyone knows, but it's better to recall. And then there will be two parts, one on the classical base Q numeration, where we have a new way of translating the solution of a Mahler equation. We will see what it is into a weighted automaton, and then we will apply these new techniques to the case of to the setting of the Zeckendorf numeration system. Okay, so let's go on. So let's start with the numeration system. So for us, a numeration system is just a pair made of U, a sequence of integers, and B, a set of digits. And in such a way that, yes, we have a constraint that the first element of the sequence must be 1 in order to be able to express any integer. And then we have a digit set which is large enough such that for any integer n, we have a sequence of digits bk up to b naught in B, such that n is equal to the summation of the bi ui. Yes. So this gives us what is called a representation or an expansion of the number n. And among all these representations, there is the canonical one, which is the greatest for the lexicographic order. So usually we write in that way. So we with parentheses with bracket. No, not bracket. Yes, we use U, which is the canonical expansion or representation of n. And then conversely, for any word, even if it's not the canonical expansion, we use a square bracket to denote the value of this word in the system U. So this is this sum of I up 0 to k of bi ui. Okay, let's so the most classical one is the base Q numeration system for Q larger than 2. In that case, the sequence Q is just the sequence of powers of Q. 1, Q, Q square, and so on. And then the digit set is, of course, the integers from 0 to Q minus 1. And for instance, just to be sure that for Q equals 3, the 3 expansion of 26 is 2, 2, 2, because 26 is twice 9 plus 2 times 2 plus 2. I think everyone knows this. So let's move to the Zeckendorf numeration system, one of the most well-known numeration systems. So instead of taking the powers of Q, we take the Fibonacci numbers, and just to have only one occurrence of 1, we shift a little bit the sequence. So we start with f minus 2 being 0, f minus 1 being 1. And then the next is always every Fibonacci is the sum of the 2 previous ones. So it gives the sequence 1, 2, 3, 5, 8, 13, and so on, as usual. And then the Zeckendorf numeration system is this sequence of Fibonacci numbers, starting from 1, 2, and so on. And then the digit set is, of course, 0, 1. The canonical expansion is the one where which is the lexicographic, or which is the greatest for the lexicographic ordering, which means here that it has no occurrence of 2 consecutive ones. So let's look, for instance, at 61. It can be written as the sum of 34, 13, 8, 5, and 1. But of course, for instance, it's also the sum of, for instance, 13 and 8 sum up to 21. So we have 34, 21, 5, and 1. And again, if we replace 34 and 21 by 55, we get 55, 5, and 1, which is the canonical expansion of 61 in the Zeckendorf numeration system. Now that we have defined this numeration system, we can start with automatic sequences. So it's a well-known definition. So a sequence taken values in a finite set is called automatic. U automatic for a numeration system U if there is an automaton deterministic which if fed with the canonical expansion of n gives as output the value of n. So the output is attached to states. So for instance, the most classical example is the 2 Morse per sequence. So an is the numbers of ones is the binary expansion of n modulo 2. And this little two-state automaton computes this. So always the input alphabet is in blue. So here we read binary sequences. So the alphabet is a 1, and of the output alphabet, so the values of n are always in red in my talk. And here this is the little arrow with 0 and 1 attached to S and T. So for instance, if the n is 17, so in binary it's 10001, and then starting from the initial state S, we can read 1 by going to T, and then using the self loop on T with 0, we can read the 3 zeros in a row. And then reading again 1, we can go back to S. And then the output in S is 0, which means that A17, sorry, is 0. And of course, because the number of ones is even in 1001. Okay, so this is the definition of the notion of automaticity. So here we use the binary expansion, but we could use any other numeration system. Of course, the input alphabet of the automaton must match with the digit set of the numeration system. So we can now start with the past. So the Crystal's theorem states that a sequence of elements in a finite field, Fq, of course Q must be then a power of a prime number, then An is Q automatic for the Q given here, if and only if the power series, the sum of n to the xn, is algebraic over the field of rational functions in X. This is a really nice theorem because it relates the notion of being algebraic, so really an algebraic notion with the notion of computability, model of computation, here automata with output. So it's quite a really nice theorem. Here I give below an example. If you take the Catalan numbers, which count the number of trees usually, but here we don't care. So it's well known that if you take the power series here with integers coefficients, then this power series satisfies this equation x y. So if y is replaced by this, then xy squared minus y plus 1 is equal to 0 over the field of the rational numbers. And of course, taking everything modulo 3 gives the power series of Cn modulo 3 with the same equation, just -1 has been replaced by +2. And then this is the same equation, but then over the field F3. And from the theorem, we know that since this power series satisfies this equation, this is the root of this polynomial, with coefficient having x, because the coefficient can be rational function, so multiplying by everything you can get polynomials. And then we know that this sequence of Cn modulo 3 is 3 automatic. And actually, I give you just below a small automaton with 5 states. So still the input alphabet is in blue. This is 0, 1, 2. And the output of the states are given in red inside the states, because the name of states do not matter. So the input, the starting state is this one with the little incoming arrow. And then we see that, for instance, if we read 1, we see that the output is 1. So C1 modulo 3 must be 1. Actually, this is true because C1 is 1. Okay, so let's so this theorem, as I told you, is really nice, but it has still a few drawbacks. First, it only works if the numeration system is a power of a prime, so you cannot take q equals 6, for instance. So we would like to have a generalization of Crystal theorem to all Q-automatic sequences, not for powers of prime. So I spoil a little bit. The answer is yes. And also, this is what we have tried to do with him. Is there a version of this Crystal theorem, or is there an extension to the setting of the Zeckendorf numeration system? And the answer, as we will see, is again yes. Okay, so first I will explain how to get rid of this constraint of having a power of a prime, and also the fact that the sequence must be finitely valued, because it takes values in a finite field. So yeah, I have an example of the composition of the equation, but I think it's not so interesting, so I will skip this example. This is for the two-Morse sequence, so we can see at the end the two-Morse sequence. If we take the power series f of x, then it satisfies this equation, x f of x equals 1 plus x times f of x squared plus 1 plus x to the fourth f of x fourth. Actually, here it's a little misleading, because f of x squared should be read as f of x squared. But as we will see in that for f2, it is the same, because here we look at everything in F2 modulo 2. Okay, so let's move on. So first, it was the work of Jean-Paul Alouche and Jeffrey Chalit, the fact of introducing U-regular sequences. So I recall the definition of U-automatic, and here we have U-automatic, and if and only if the sequence can be computed with a deterministic finite automaton, and the notion of U-regular. So it's a sequence here. We don't need to take values in a finite field. It can be values in any commutative ring R. And then the sequence is said to be U-regular for the system, numeration system U, if and only if there is a weighted automaton, we will see what it is, whose output which computes A of n when it is fed with the canonical expansion of n in the numeration system U. And actually, this is really the right extension of Christoph's, of the definition of automaticity as a sequence which is Q-regular and also takes finitely many values, actually is Q-automatic, and the converse is straightforward. So we have this notion of U-regular. So before explaining what is a weighted automaton, I will give you some examples of few automatic sequences. Here I will take Q equals 2. So here are a few examples of two regular sequences. So for instance, instead of taking the number of ones in the binary expansion of n modulo 2, we take really the number of ones in the binary expansion of n. And then it defines a two regular sequence. We will see how to compute that. If you look at the numerators of the endpoint of the contour set, it is also two regular. If you take, for instance, n to some fixed power j, then it is a two regular sequence. And as it is easily seen, it can be easily seen that regular sequences are closed by many operations, namely they are closed under addition, and therefore any sequence given by a polynomial is actually two regular for the same reason. And also, if you take sum of logarithms, it is still Q regular. This is more or less, instead of counting the U, you count the number of digits, more or less, in the expansion. And also a more computer-oriented sequence. If you look at the number of comparisons in the merge sort, then it gives a regular sequence. And an interesting example, which we will come back at the end to it. We will come to it at the end again. Then if you take a real number a and you look at the powers of a, so the sequence a to the n, then it is Q regular if and only if either a equals 0, which is trivial because the sequence is identically 0, or if a is the root of unity. In that case, the sequence is periodic, and then it is trivially Q regular. Actually, it is even automatic because it has then finitely many values. So I have to explain you what is weighted automaton. So the idea is to have an automaton which is maybe non-deterministic, as the example, and which has weights. So weights means here that we have weights as we have initial weights for states. For instance, the initial weight of S is 1. This is the little incoming arrow with 1. Yes, weights are red always, and incoming digits are, so the digits are always blue. So we have a little incoming weight for S, which is 1, and there is no incoming weight for T, so this is implicitly 0. And we have also final weights. So the final weight of T is 1. This is the little outgoing edge. And the final weight of S is 0 because there is nothing written. And then we have also weights for transition. So each transition is equipped with an input digit and a weight, always with a colon in between, in my example. And then, so we have a function which assigns to each transition a weight in R, and the same with a function which assigns weight, an initial weight, and another one which assigns final weights to states. And then so this is the machine, how it works. We will see that on an example. The idea is that any run or any pass in this automaton has a weight, which is the product of the initial weights of the first state, the weights of each transition used along the path, and then the final weights of the last states. And then, so it gives a weight gives a weight to each path, and then the weight of an input word is the sum of all weights of all the runs. So we will see in this example that, so I take the same example as before, and then we take the word 10110, which is the binary expansion of 22. And then the field is again the finite field F2. And then actually we are looking at all runs labeled by this word, but actually since the only state with non-zero initial weight is S, we start the runs starting in S, and since the only state with non-zero weight final weight is T, we start runs ending in T. And then we have 3 runs. Actually, we have to choose which one is used to go from S to T. For instance, we can either start in S and then with the first one move to T and then remain in T until the end, or in the second run remain in S until the second one, then we move to T and then remain in T, and this last one we remain in S until the last one, and then we move to T with the last one, and then we remain in T. And then we have these 3 runs. Each of these runs has weight 1 because we have only weights equal to 1. And so the sum of these weights is 3 in N, but F1 is F2. And actually, we can see that this little weighted automaton computes also the sorry, I missed the word, the tumor sequence, sorry. So this is weighted automaton also compute the tumor sequence, but in a different way, not as the deterministic ones we have seen before. We have to, since we are not in a finite field, the equations we will look at will be quite different. We will look at what is called the Mahler equations. So actually, the idea is that we have a commutative ring R, and then if we are in the base Q, and therefore we look at the linear operator, which maps its rational series to the rational series obtained by replacing x by x to the q. And so this is a linear operator that can be, of course, iterated. And if we have polynomials AI, we look at such an equations, the sum of AIs of x phi to the I of y equals 0. So it's an equation in P, in x and y. It's not really a polynomial because phi is not a polynomial anymore, but it has the flavor of it looks like a polynomial. And we call that such Mahler equations. And we said that f is Q Mahler, or if it satisfies the Q Mahler equation. So if we replace y by f of x, then it should be equals to 0. And then the function, the power series is called the Q Mahler. So it looks different from algebraicity, but actually in finite field it's quite the same, because if we have a power series like this, so the sum of fn x to the n, and if we raise that power series to the power q, and we are in the field fq, then of course it's because we are in the finite field fq, the sum of to the power of q is the sum of the element to the power of q, so we get fn to the q x qn, and also fn to the q in fq is equals to fn, and therefore we get exactly the same power series where x has been replaced by x to the q. And this is why actually this linear operator mimic in the case of fq the raising the power to the power q, the power series. And then I recall you the Crystal's theorem, and so we have Q automaticity is equivalent to being algebraic of FQ, and it has been extended to the setting of regular sequences and weighted automata by more or less at the same time by Becker and Dumas. And the statement is not anymore if and only if. It's two implications. So we have first that if the sequence UN is Q-regular, so which means computed by a weighted automaton, then it is a solution of a Q-Mahler equations. So it is the same as Q-automatic implies algebraic. So this is not the same, but the extension of this statement. And conversely, if we have a solution which is if we have a power series which is the solution of an isolating Q-Mahler equation, then it is co-regular. But of course, we need the equation to be isolating, which means that the coefficient in front of y is 1, which means that the equation is really of the form y equals a sum of polynomial times iterated application of phi to y. Okay, so the proof actually of Becker and Dumas, it's really inspired by the proof of Kristall's theorem. And what we have done with him is to provide an alternative proof from equation to automata, to weighted automata. Actually, the idea is to use a different way of constructing the automaton. We don't use anymore the Cartier operators. We build directly the automaton from the equation. And actually, what we have found is that there is what we call a universal automaton. Actually, this is an infinite automaton with countably many states and transitions. But actually, this is a uniform, more or less, automaton. And for any equation with finitely many coefficients, actually, only a finite part of this automaton is useful to compute the solution of the equation. So we have this universal automaton with S being infinite, countable, but for any such equation, we use finitely many states. Actually, only finitely many states are useful to compute the weights. And actually, as we will see, the coefficient occurring in the polynomial of the equations are used as weights of this automaton. So instead of giving a formal definition, I will give an example. So suppose we start with this equation. So an equation of 8(3), which means that the polynomials used A1 and A2 are of degree 3 and exponent 2, which means that we have only phi of phi. So here we are in base, we use two Mahler equations, so Q is 2, and phi f of x to the 4. Okay, and then I have drawn only a finite part of this universal automaton. But actually, you have to imagine that we have infinitely many lines and infinitely many columns. So it is more or less like a grid of states. And we have the number of useful lines is actually the exponent, because here the exponent is 2. We only need these 2 lines, but you could imagine that you have more lines in the automaton. And since the degrees of the polynomials are up to 3, we need only 3 columns in the automaton. And as you can see, so here we are in base 2, so the input alphabet is in blue and it is 0, 1, and the weights of the transition are always coefficients coming from the 2 polynomials A1 and A2. Okay, and as you can see, the automaton is quite regular in the sense that it's easy to predict what you have. So so it was for an equation of A3 and exponent 2. If we move to an equation with only exponent 1, which means that we have only a1 and a2 is no 0, then we only need one line of the automaton, and everything is gray, is not useful anymore because the coefficient that we use have become 0, or maybe not exactly all coefficient because we had the 1 here, but you can check that you have no path that use the state S11, this state, and which has a non-zero weight. We can prove that actually, that only these three states are useful in the universal automaton. So our construction is new, and what we like in this construction is that instead of using Cartier-Foucault operator, which more or less read input from right to left, which means from the least significant digit to the most significant digit, here we really read the word, so the expansion of the number from the most significant digit from left to right, from the most significant digit to the least significant digit. And as you will see, the F0, which is the first coefficient, of course, the equation is linear, so you can multiply everything by some constant. It doesn't change the solution. So the equation and the solution remain the same. So the first coefficient data is used for the weights of the initial weights of states. And this is in the first column, and only one state is final and has weight 1, which is the state in the upper left corner, the state S00. Okay, so it was our contribution to give this new construction of the weighted automaton. And actually, we needed this to use it for the Zeckendorf numeration system. And now I will move to this new setting. So let's move to this Zeckendorf Avenue Boulevard. So what we have obtained is the following. So I recall the Becker and Dumas theorem, which says that if a sequence is regular, then the attached from power series is a solution of a Q-Mahler equation, and conversely, with the restriction of the equation being isolating. More or less, we have exactly the same, but we have to replace Q regular by Z regular and Q Mahler by Z Mahler. So it's more. It looks like search and replace statement, but actually, as we will see, so that there is a few things to change. So Z regular, this is actually straightforward. This is exactly what should be expected. So we look at weighted automata, but instead of feeding the automata with binary or expansion in base Q, we feed the automaton with the Zeckendorf expansion of the integer n. We will see an example later, but now I have to explain you what it means to be a Z-Mahler equation, and I will move to that. So to explain exactly the idea of what we have done, so the idea is that we have replaced the operator phi that we were using let's come back to this. So we had this operator phi, which no, sorry, I've clicked. We had this operator phi, which replaced x by x to the q. And actually, we will do something similar, but a bit different. So we have to replace the map which maps m to qm, so replacing x to the m by x to the qm, and to define the appropriate notion of Z-Mahler equation. And the idea is as follows. So if you're in base q, multiplying by q is just adding a 0 in the expansion of the q expansion. And the idea was to mimic this and to take as definition, we take an integer n, and we suppose that its Zeckendorf expansion is w, or word w over 0, 1, with no consecutive ones. And then we add a 0 at the end, and we take again, so it was in base q. So yeah, it was in base q, but our idea was exactly to do the same. So we suppose that the Zeckendorf expansion of n is w, and then we map. So the function that we use is called little phi, and little phi of n is the Zeckendorf value of the word w0, and actually it gives that, for instance, if the n is a Fibonacci number, it gives you, of course, the next Fibonacci number. So 1 is mapped to 2, 2 is mapped to 3, 3 to 5, and 5 to 8, and 8 to 13, and 13 to 21. But for instance, also 4 was expressed as 3 to 1, and then when you so the expansion was 3, 0, 1, and then we map 4 to the 5 plus 2, which is 7, and the same with 6, which is 4 plus 2, and so on. Okay. So this map since is well defined and it looks nice, but it has a main problem is that the map which maps the function which maps n to qn is of course linear, but the map phi is not linear at all, not linear. For instance, f of 2 is 3, which is not the sum of 2 times f of 1, which is 4. And actually, it was a problem because more or less, when you multiply a power series, you add an exponent. And since we will use this function little phi in exponent, it will make a problem. Actually, the idea was to see that this function is not linear, this little phi is not linear, but as we will see, it's almost linear. So we introduced what we call the linearity defect. So we look at the difference between phi of n plus n minus phi of n, phi of n, and actually it just an application of Binet's formula that you can check that this linearity defect is always between -1 and 1. So it only takes 3 values, -1, 0, and 1. This is why, and this is a small value. This is why we say that phi is almost linear. Actually, you can see that little phi is almost multiplying by the golden mean. This is why we have that the fact that the linearity defect remains small. And actually, we have more on this linearity defect. First, it is small, so always between 0 and 1. And furthermore, as we will see, it can be computed by a deterministic automaton. So we use a classical result of Christian Frugny that if you take for instance, the Zeckendorf expansion, of course, it's more general. It's true for numeration system based on a Piso number, that if you take some finite alphabet, which is contained in Z, so with positive and negative integers, and you look at words which evaluate to 0 in that with that digits, then it is a regular set of words or finite words. So for instance, if we look at C made of 0, 1, and -1, then for instance, the word 1, -1, -1, 0, -1, 1, 1, 0, of course, it's easy to check that the 1 here cancels with the 2 -1 on the right, and the same here, the -1 cancels with the 2 1 on its right. But here it's less easy to see that the 1 cancels all the -1 on its right. But then still these two words have value 0. You can check. And then Christian Frugny proved that this set of words having value 0 is a regular set of words. And actually, we use that result to show that the linearity defect can be computed as follows. If you two integers m and n are given in their in their Zeckendorf expansion, then we have a deterministic automaton that reads both of them and then gives in his final in the last state the linearity defect with the value -1, 1, and 0. Okay. And then now you have maybe an idea of what we have done. So we have introduced this function little phi, and then we mimic the definition of the big phi of Q. We define our new Z-Mahler operator big phi from power series to power series, which map up some f of n x to the n to f of n x to little phi of n. And then we use this linear. Of course, it is linear by definition. And then we said that such an equation where we have here the AIs are still polynomials, and we have this use or iterated use of this new operator phi. Then we call this such an equation a Z-Mahler equation. And we said that power series F is Z-Mahler if and only if it satisfies a Z-Mahler equation. So it is the root of such an equation. Actually, it's not really a polynomial, as I said before. It looks like a polynomial in phi. Okay. And actually, what we proved is more or less again an extension of Becker and Dumas results. So we have proved that if you take a sequence of values in a commutative ring R, then the sequence is Z regular if then sorry, it's not a if and only if. If the sequence is Z regular, then the power series is the solution, is a Z-Mahler equation. It's not exactly the sequence of the power series. And conversely, if the power series is the solution of an isolating Z-Mahler equation, then it is Z regular. So what was interesting is that so our construction of the automaton from the equation was quite different from the one used by Dumas and Becker, but actually we came up with the same restriction. Actually, our construction of the universal automaton assumes also that the Z-Mahler equation is isolating. So we have exactly the same restriction of being the equation being isolating. So here I gave you of some sequence which is Z-Mahler. So instead we take an, the number of Zeckendorf expansion of an integer n. And if we look at this powers series, so the sum of an to the x to the n, you can easily see that it is this infinite product. And using this product, you can, when you apply big phi, it will shift all the f to fn to fn plus 1. And therefore, you can see that f of x is actually equals to the product of 1 plus x times the f applied to f of x. So f is the solution of this Z-Mahler equation, really simple one equation. And actually, you have here a weighted automaton which computes exactly an. Actually, you can check that for each input word, the number of runs from R to R is exactly the number of Zeckendorf expansion. Actually, we use in different way the automaton given by Christian Fruni to compare the canonical expansion to any other expansion to check that the difference is 0. And this is why we have one run for each Zeckendorf expansion. And since each run has weight exactly 1, because all the weights are 1, so all runs from R to R, because the initial and final weights of S and T are 0. And then since all weights have weight 1, the sum of these weights is exactly the number of Zeckendorf expansion of n. Actually, we have cheated a little bit because we started from this equation, but we could have given you the one given by the universal automaton, but the problem is that in this setting, we have to expand the universal automaton with the automaton computing the defect, the linearity defect, and actually the automaton is, even for this small equation, the automaton is huge. So this is why we have given this automaton and not the one given by our construction. So it's what we have obtained. And I will conclude with a few open questions that we have. So any hints or even solutions are welcome. So for instance, just looking at which sequences of that form which are Z-regular, we have not been able to prove, of course, if A is 0 or a root of unity, the sequence is ultimately is periodic, and therefore it is easily seen to be Q-regular. But conversely, we have not been able to show that if such a sequence is not Q-regular, Z-regular, sorry, if such a sequence is Z-regular, does it imply that A is 0 or root of unity? We have looked at the proof. It uses van der Monde determinants, and it does not fit well at all with Fibonacci numbers. So we are, and actually, this is interesting, just this characterization of such equations, because it is used more or less in the second result, because as we have seen, as in the case of Becker and Tuma, we have a gap between Z regularity and being Z Mahler, because here we only need being a solution, and here we need an equation which is isolating, and it's not always the case. And actually, the gap has been closed in the case where the field is the field of complex numbers. And then they have a complete characterization of a series which are Q-Mahler, and it uses the root of polynomial, and the roots of unity have an important role in this characterization. This is why it would be interesting to see whether it is still true that only for root of unity it is Q-regular. Of course, we would like to extend this kind of result to the Zeckendorf numeration. Actually, already in the work of Becker, there was an example showing that if the equation is not isolating, it may happen that the solution is not Z-regular. And we have also an example in our setting. Actually, we have a different way of proving that the solution is not regular. We look only at the growth rate of the coefficient, because it can be seen that if the sequence is not Z-regular, the values of the sequence cannot grow too fast. And actually, we have an example where it grows too fast, and it is the solution of Z-Mahler equation. So, of course, we would like to have a complete characterization of series which are solution of Z-Mahler equation. in when the field is C or even more. And of course, we also would like to move to Cobham's like theorem. So the Cobham theorem states that if two sets of integers or k automatic and L automatic for k and L being multiplicatively independent, which means that the expansion of base k and their expansion in base L give regular sets of words. Then it is well known, Cobham's theorem states that then this set of integers must be ultimately periodic. And then there is an extension due to Adamczewski and Bell and Sheffield and Singer, showing that in the case of K and L Mahler equation, when the characteristic of the field is 0, then they can show that the series is actually rational, which is the natural extension of being ultimately periodic for sets of integers. So this, for the case of integers, of course, there has been work by Durand showing that we can extend the Cobham's theorem to K regular and also regular for some Piso numeration system. And we would like to have such a result for solution of K Mahler equation and Z Mahler equations. That's all. I would like just to conclude, to make a comment, just to answer a natural question, is that, of course, we did it for the Zeckendorf numeration system, which is the simplest one for Piso numbers. But actually, what we use is more or less the fact that addition can be made in this numeration system. So what we have done can be extended to all numeration system based on a Piso number like Fibonacci or other numeration system. Then I will stop here now.
Thank you very much, Olivier. Does anyone have any questions? So I guess you, well, you answered my obvious question right at the end there. So I guess somehow this almost linearity will just hold for any of those numeration systems where you have the addition.
We think it's, of course, it will become a little, because it uses Binet's formula, such a result should also hold. Of course, the value will not be anymore just -1, 0, and 1, but and also the techniques of Christian can be used to get an automaton that computes this linearity defect. We have not made really the computation, but we are convinced that it should go well. Of course, the problem is that already, even for the Zeckendorf numeration system, the definition of this universal automaton is quite complicated. We have states indexed by 4 objects, and adding also the Piso numbers would add one. Makes everything more complex, but yes, of course it should be done, but we are quite convinced that it should work well.
Does anyone else have a question for Olivier? All right. If not, thank you very much, Olivier, for your talk.